Hello everyone and welcome to our final presentation. This is Team 12, Analysis and Redesign of an Optical Microscope. The BN107 is a binocular biological microscope designed for lab and educational use, offering a total magnification range of 40 times to 1600 times. These microscopes are used to analyze and view objects not visible to the naked eye, commonly used in the study of cells, tissues, and material microstructures. It is manufactured by multiple companies, including Opto EDU with 60,000 units per year and FY Microscope with 50,000 units per year, yielding at least 110,000 units manufactured yearly. This is our exploded CAD view. As you can see, we have 19 unique parts, excluding fasteners.
The primary customer is professional scientists and researchers who use the microscope daily and require reliable performance, increased magnification, and 2 eyepieces for an easier viewing experience. A secondary customer is educational institutions such as high school and college students. The secondary customer values a low-cost, durable, and easily portable microscope for the classroom. The main function for the microscope is to analyze the specimen of interest in the FAST diagram. The basic functions are to magnify the image and illuminate the specimen. From this, it includes focusing the image, selecting magnification, and then for illuminating, the product needs to generate, transmit, and control the light. The supporting functions are assure dependability, assure convenience, enhance product, and please senses, which are then branched out further into other functions.
This function component mapping matrix highlights the role each part plays in the overall system. Our redesign efforts are primarily focused on the head cover, eyepiece, and the top-bottom stage subassemblies, since these parts contribute most directly to usability, alignment, and overall system performance.
Moving into product family design, this is our functional differentiation table. As you can see, most of our functions are the same for both customer groups, and we have 5 that are different. Select primary power, enable stereoscopic viewing, amplify primary image, and reduce strain are all functions that are more relevant to our primary customer group, whereas enable portability is more relevant to our secondary customer group.
This is the component commonality table for the primary and secondary variant. The main difference between these two is that in the secondary variant, it does not have the 100 magnification lens module. It has a singular eyepiece and only a 3-prong lens rotator instead of a 4-prong lens rotator. This slide shows the function component mapping associations between the primary and secondary consumer modules. As you can see, the researchers and scientists will be paying more for their stereoscopic view with the 100 magnification lens and the dual eyepiece, whereas the secondary consumer modules only include a 3-prong lens rotator and a single eyepiece. In these pictures, you see the CAD visualization of the component designs for the primary users on the left and for the secondary users on the right. In this slide, we see the common interfaces between the platform components and each module component that allow plug-in of modules for the primary product variant. This is the modified feasible assembly sequence for users of each variant. This assembly sequence realizes delayed differentiation because only at the point of assembling the eyepiece and lenses subassemblies, they will begin to differ.
Cost calculations were done for the original product, and then design for manual assembly was performed on 2 parts to reduce their individual cost and therefore the cost of the overall product. The head cover, which performs the function of protecting the optics, was selected for redesign because in the quadchart this part was found to have high manufacturing and assembly cost, but relatively low importance. The eyepiece assembly, which performs the function of amplifying the image, was also selected for redesign because being a duplicated part in the original design presented the opportunity to reduce material and assembly time by half by redesigning for only a single eyepiece. These redesigns had a significant impact and roughly halved the material cost and assembly cost of both parts, as shown by the costs in the table on this slide. The reduction from $256.32 to $255.63 was small because the highest costs in this product are from the purchased components. However, this is still a valuable reduction when considering production at a large scale.
We redesigned the stage subassembly for automated assembly. We noticed from the quad chart that the stage subassembly has high functional importance, but room for lower cost. Before redesign, the stage subassembly has a handling cost of 30.6 cents, an insertion cost of 16.2 cents, and a total unit assembly cost of 46.8 cents. We used guidelines DFA 3, 6, 8, and 5 to redesign the stage subassembly. After redesign, the handling cost was 16.2 cents, the insertion cost was 13.32 cents, and the total unit assembly cost was 29.52, which is less than the original cost of 46.8 cents, which saves about 17 cents for assembly cost.
For our redesigned head part, we identified 3 critical dimensions highlighted in red based on functions from our function component mapping matrix. The 4 through holes where fasteners are secured were assigned a very approximate tolerance of plus or minus 0.05 millimeters because they are critical to the function of supporting components, as these fasteners will stabilize and secure the head to the rest of the body of the microscope. Similarly, the length and width of the top eyepiece mount were assigned an approximate tolerance of 0.05 millimeters as well, because they support the function of enabling stereoscopic viewing by providing a stable connection for the eyepiece. All other dimensions have a standard tolerance of 0.5 millimeters. The critical dimension for the head cover was identified as the radius of the snap-fit extruded spheres. This dimension correlates with the function of protect optics, as the head cover snap-fits into the head to provide a secure attachment. However, all dimensions of this part were given the standard tolerance of 0.5 millimeters, as none are vital to microscope stabilization or require precision for fasteners. Our recommended material for manufacturing the head is aluminum alloy 6061T6, as it is stiff and durable and compatible with fasteners. Based on shape, tolerance, and other considerations, the process compatible with this aluminum alloy was narrowed down to machining as justified by the table. Our recommended material for the head cover is ABS thermoplastic, as it is low cost and easy to process. Based on the same considerations as the last part, the manufacturing process that was chosen for this part is injection molding.
The head part that holds the eyepiece was analyzed with DfM Pro for design changes to improve manufacturability. The updates include removing the flat bottom holes with conical bottom hole, and then also making the small holes around the edge through holes to also help with tool accessibility. Rounds were also added to the internal corners. Some impacts to the design is that the small through holes negatively impact the overall look of the microscope, and it could introduce an area for dirt to accumulate. But from these improvements, the machining cost decreased, which had an overall of 82 cents in cost savings. The head part was then analyzed with hubs and extrapolated to get a unit price for a larger batch size. When comparing the analytical method to the cost of the machining found by hubs is lower than the analytical cost model due to the bulk discount and the production and suppliers in lower wage countries, as well as very long range extrapolation. The head cover was updated for injection molding with a cavity core mold design, by making the wall thickness uniform throughout, adding a 5-degree draft angle and rounded corners. When comparing the cost of before and after the redesign, the majority of savings came from the machining cost, with a large decrease in cooling time, with the max thickness going from 12 millimeters to 3 millimeters. Overall, this design update has a positive impact to make the design sleeker and reduce material, as the underside is not seen by the consumer, and it resulted in a 58-cent cost saving.
This lets users directly stream images and videos to their phones or computers. Through our Microscope Plus app, students can capture, save, and annotate their observations, while teachers and researchers can easily share findings, track progress, and work remotely. Overall, this approach reduces school costs, cuts environmental waste, extends the microscope's lifespan through software updates, and greatly improves accessibility for remote and hybrid lab sessions. In conclusion, we meet our goals of reducing part count, simplifying assembly, and lowering manufacturing costs. However, some parts remain overly complex and difficult to orient during automated assembly, and users currently lack a clear way to verify alignment of internal components. To address this, we would propose redesigning key parts with simpler, more symmetric geometries to improve handling, and adding visual alignment indicators to ensure proper positioning during assembly and use.